So first, I'd like to thank the organizers for giving me the opportunity to visit this institute. This is my first time to be here. Actually, I was invited 2 years ago. What's this? Oh, okay. So I was invited 2 years ago, but I was unable to come because, 2 years ago, corona pandemic was still all the rage, and the border control was so mess, so I actually gave up. But I'm very happy to be here. And since this is the first French-Japanese joint conference on these topics, I'm very honored to be the first speaker of the very first meeting. Thanks, Fukushima-san. And I hope that this event is going to continue for many years to come, but it depends on the budget, I guess. So I'm going to speak about applications of Markov chain Monte Carlo methods. Let me explain the motivation first. You can see those subtitles up ahead and the number of pages. So I'll try to contain my talk in 45 minutes, but most likely I will fail. So what I'm interested in, not only me, but also many others are also interested in, is to find the ground state of the following Ising Hamiltonian. So each vertex, so on a finite graph, so each vertex has a spin variable sigma x, which takes either +1 or -1, and the energy is defined by this. So the Hamiltonian consists of two parts, two body parts and one body part. The coefficient in the two body part is called spin-spin coupling, and if this is positive, we call this ferromagnetic spin coupling. If it is negative, we call antiferromagnetic spin coupling. Hx is kind of biased. It's called external magnetic field imposed on the vertex x. And we are trying to find a set of spin configurations. It's flashing, actually. Sorry. So it's a set of spin configurations in which this Hamiltonian takes its minimum value. So this is a simple, maybe the simplest, not simplest, but maybe relatively simplest example. Suppose that the graph consists of two vertices and consists of one edge, and each vertex has a spin variable which takes either plus or minus. So the number of spin configurations in this space would be 4, because we have two vertices, and each vertex has two values. So we have up, 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 down, down, up, and down, down. So there are 4 elements containing the space, spin configuration space, and we plot all the value of h for each spin configuration. For example, if I plot in this way, then what we are interested in is the collection of spin configurations at which the Hamiltonian takes its minimum value. So in this situation, these two spin configurations form GS. The reason why we are interested in this problem is because there are many combinatorial optimization problems. So I listed some of them, but one of them is the so-called max cut problem. So we are asked to divide the vertex set V into two sets, S and its complement, so that we can maximize the sum of the weights of the cut edges between those two sets. So in this situation, there are 4 possibilities. S could be empty, or 1, or 2. In this situation, it would be the same, and V. And we are trying to maximize this. Let me more precisely. So let Wxy be the weight on the edge xy. And what we want to do is to maximize this C. C is the sum of the weights on the edges, but x has to be in S and y has to be in the complement, or vice versa. So if we introduce this spin variable, sigma x, which is either 1 or -1, depending on whether x is in S or not in S, then we can rewrite the C in this way. So if you want to maximize the value of C, it is corresponding to minimizing this Hamiltonian. So you can ignore this multiplicative constant 1/2, and you can also ignore the effect coming from this 1, and minus sign is cancelled to get this Hamiltonian. So as I said, here we have negative sign in front of the sum. We do not have here. So if we extract minus sign in front of the sum, you will have minus W, and W is not negative. So in this situation, minus W is negative, so this corresponds to the antiferromagnetic Hamiltonian. So finding an optimal solution would correspond to finding a ground state of this Hamiltonian. So there are other combinatorial optimization problems. Famous one would be traveling salesman problem and knapsack problem. But those problems are usually difficult because the phase space is humongous, is quite large. In this situation, we have only 2 vertices, so the number of spin configurations would be 2 to the power 2. It's just 4. But if a graph consists of 1,000 vertices, then the number of spin configurations you have to deal with is 2 to the power 1,000. It's huge. You wouldn't be able to list up all those values of the Hamiltonian and compare all those values and try to find the minimizer. So it's very complicated, potentially. But if the spin-spin coupling is positive and the external magnetic fields are all positive, then it's not that difficult to find the ground state. In that situation, all spins pointing in the same direction as the external magnetic field would be the unique ground state. But as soon as you introduce negative spin-spin interaction and negative external magnetic field and positive external magnetic field, the energy landscape gets really complicated. And you won't be able to tell which spin configuration will be the ground state from the first place. So this is the second complication due to generality. So people usually use Markov chain Monte Carlo methods to sample the Gibbs distribution pi, which is proportional to the Boltzmann factor e to the power minus beta h. So beta is the inverse temperature. In my abstract, I was using 1/T instead of beta, but they are the same. So if you can sample this distribution, if beta is very large, then this probability distribution concentrates around the ground state. So you might want to use this Markov chain to, how can I say, capture the ground state of the given Hamiltonian with high probability. That's what they usually do. But unfortunately, conventional Markov chain Monte Carlo methods based on a single spin flip dynamics like Glauber dynamics and Metropolis algorithm. So in my talk, I'm going to explain what the conventional Markov chains are, like Glauber dynamics and Metropolis algorithm, and compare them with the relatively new Markov chains. One of them is called digital annealer, which was invented by Fujitsu Laboratories in 2017. Another one is stochastic cellular automata, and the last one is its variant called Iona SCA. And at the end of the talk, you'll be able to understand, you'll be tell which one is better than the others, at least in practice. So do you understand the motivation? I would like to find the ground state of the Ising Hamiltonian. Okay, so let me explain the conventional Markov chains. So let me use this notation, sigma x and nabla x plus h. So sigma x is a spin configuration which is almost identical to sigma without superscript x, except for at vertex x. So at vertex x, sigma x points in the opposite direction as sigma. Otherwise, they are pointing in the same directions. And I use this notation to define this nabla h. So this plus means we are taking the positive part of the energy difference. So when we introduce spin flip at vertex x, if the energy increases, then the difference is attained as the value of this nubula. If this spin flip induces a negative quantity here, then we attain 0 as a value of this nubula H. Then there are two Markov chains. One of them is called Glauber dynamics, and the other one is Metropolis algorithm. They are both almost the same. There's only one difference in the acceptance probability. So you can see this is the transition probability from sigma to tau in a single step, and the tau is allowed to be either sigma or sigma x. So if the Hamming distance between sigma and tau is bigger than 1, the probability is 0. So it's both transition probabilities are based on single spin flip rule. So let me use this figure to explain, to interpret this transition probability. First, so here we have this 1 over v. This means that we pick up one of the vertices in v with equal probability, 1 over v, and then choose or decide whether this chosen spin should be flipped or not, depending on the accordance, according to this acceptance probability. So the acceptance probability is slightly different between those two algorithms, but basically they are the same. Okay. The nicest thing of those two algorithms is that they are aperiodic and irreducible. So aperiodic means that the greatest common divisor of the period is just 1. And also irreducible means that any pairs of spin configurations are communicative. After several steps from sigma to tau can be reachable, and vice versa. And the most important thing is that this transition probability satisfies this detailed balance condition. So detailed balance condition is this identity for any pair of spin configurations. So you have this Gibbs distribution and the transition probability. This bullet is either G or M. G for Glauber, M for Metropolis. This identity holds. It's not that difficult to check this identity because for Metropolis algorithm, since the transition probability is proportional to this one, and the both Gibbs distribution is proportional to this one, you multiply those two terms and then combine the exponent, then you will get this max between H sigma and H sigma x. It's symmetric with respect to the swap between sigma and sigma x. So you have this identity. This identity is a kind of, it's a sufficient condition to tell that pi is the stationary distribution with respect to this transition probability. I'm not sure, is my voice heard? Okay, so since we have aperiodicity and irreducibility, actually this pi beta is the unique stationary distribution with respect to this transition probability. So after n steps, it weakly converges to pi beta from any initial distribution. And in particular, this Markov chain generated by this transition probability, either Pg or Pm, if we wait for long enough, this Markov chain is in the ground in this set GS with high probability, irrespective of the initial spin configuration, provided that the inverse temperature is large enough. So this is a kind of theoretical justification that we can use this Markov chain to capture the ground state with high probability. There are other mathematical results, but I'm not going to touch these issues like mixing time and simulated annealing. This PDF file is available on my homepage. So if you want to know more in details this statement, just go there and download this file and study the elements for yourself. But I'd like to stick to this statement. So as I said, that this is a theoretical justification for the use of Markov chain to capture the ground state of the original Hamiltonian, right? So we would like to generalize this statement to a much wider class of Markov chains, so that this PGPM is based on a single spin flip dynamics. So if you want to have a better Markov chain, which might be faster or might be better in probability, that would be desirable. So we want to generalize this statement first and try to construct a Markov chain, new Markov chain. That's what we want to do. So in the next page, generalization. Okay? To generalize this statement, I have to introduce two notions in red. One of them is red function, the other one is virtual energy. So a Markov chain generated by a transition matrix P beta is said to have rare transition with red function V if this relation holds in beta to infinity. So the actual definition is actually here. But you can think of this transition probably looks like e to the power minus beta times the red function plus smaller beta. For Glauber and Metropolis algorithm, it's not so difficult to compute this red function because first you have to take the log and then divide this quantity by beta and take beta to infinity. That's minus V. Let's look at the Metropolis algorithm. So we have this transition probability. Take the log, log of 1 over V. It's not going to be important because you have to divide this by beta and take beta to infinity. This is going to be 0. This one gives us minus nabla H. So that's why we have this. If tau is on the diagonal, if tau is sigma, then this is 0. Otherwise, it's going to be infinity. That's the red function. And the second one, this is actually the most important quantity through the talk. This is called virtual energy. This is really complicated quantity, actually. It's constructed from this red function. We have to sum this red function on some... it's really difficult to tell this. Maybe I can come back to this representation, but U sigma can be constructed by using this red function. The second quantity seems to be even worse, but it's actually the minimum value of the first term. So you subtract this term so that the base point of U becomes 0. So the most important part is this one, but it is really complicated to compute this exactly. But the most important statement is the following. So if Markov chain is generated by aperiodic probability stochastic matrix having rare transition with irreducible red function. Irreducible red function means that the matrix e to the power minus v is irreducible. If those two conditions satisfied, then there is a unique stationary distribution, and that unique stationary distribution obeys this limit relation. Here we have this virtual energy. So you see, if we use this Markov chain, when the number of steps goes to infinity, that Markov chain converges uniquely to this distribution, and this distribution concentrates around the base point of this virtual energy. So we should be able to use this Markov chain to capture the argument minimum of U, the bottom of U. If we wait for long enough, this probability is large, it's close to 1, irrespective of the initial spin configuration, provided that the inverse temperature is large enough. So here it's not GS yet. So what we want to do is to find the relation between U and H, or argument minimum of U and GS. But as I said, that this is really complicated. I'm not going to probably into the exact formal expression of this, but I'm going to use this relation instead. So if we can find a function f that satisfies this identity, so we have red function, if we add this one, and if we change the role of sigma and tau as this, and still this is equal, then actually this virtual energy, you do not have to compute this thing. Actually, U of sigma is exactly equal to F modulo constant shift. This is to, I can say that the minimum point of U is 0. So as I said, that this is a generalization of this theorem 1, this one. So I'm going to derive theorem 1 from theorem 2 by using this relation in 5 lines. So we know already that Glauber and Metropolis algorithms are aperiodic and irreducible. And also, we already know that rate function for those algorithms are nabla H. If we add this to the original Hamiltonian, then because of the definition of this nabla H, this is exactly equal to the max between H sigma and H sigma x. It's symmetric. So we can swap the role of sigma and sigma x to obtain this identity. This is actually exactly equal to this, with F replaced by the original Hamiltonian. Therefore, the virtual energy is exactly equal to H, the original Hamiltonian, modulo constant shift. So argument minimum U is exactly equal to GS. That's how we can obtain theorem 1 from theorem 2. The reason why virtual energy, the expression for the virtual energy is so complicated is because I'm using this general theory of Markov chains. I'm not going into this statement today because of lack of time, but the key point is summarized as this. So if you want to construct a new Markov chain to find the ground state of a given Hamiltonian, what you have to do is to construct a rate function and the virtual energy U. And so a rate function, this is a review. V is the limit of 1 over beta multiplied by log of the transition probability. And U is, well, there was a complicated expression, but if we already know that this matrix is aperiodic and irreducible, then the equilibrium distribution is unique, so that you can characterize this U by using the equilibrium distribution. And I also mentioned this identity. This is kind of zero temperature limit of the detailed balance condition. If this is true, then virtual energy is, you do not have to compute this. Actually, this is equal to F minus the minimum of its value. So that we can say that after wait for long enough, this Markov chain reaches to the argument minimum of U with high probability, irrespective of the initial spin configuration, provided that the temperature is very low. And argument minimum U is GS for both Glauber and Metropolis. That's what we have shown, we have seen. So in the rest of the talk, so here there are 4 shaded items, and I'm going to explain what those items are in the second half of the talk. Any question up to this moment? So the motivation is to find the ground state of a given Hamiltonian. We are trying to generalize this Markov chain theory to come up to a better Markov chain to capture the ground state of the original Hamiltonian. So this is the digital annealer invented in 2017 by Fujitsu Laboratories. In their paper, there was no expression, so they didn't actually define the transition probability in this explicit formula. So, but they had numerical simulations, and then they claimed that the performance is better than the conventional Markov chains. So we started investigating this digital annealer by ourselves. And then what they were saying is that the transition probability, if we write down explicitly the transition probability, this is going to be a little bit complicated expression like this. But this can be interpreted by using the following figure. What we do is the following. Let me go back to this. The conventional Markov chain. So in Glauber Metropolis, we first choose one of the vertices with equal probability and then decide whether this chosen spin has to be flipped or not, depending on the acceptance probability. In DA, oops, okay. Up. We changed those two steps. So we first, how am I supposed to, it's not a flip, but I'm going to say that. So first we flip all spins independently. So this is not flipped according to this acceptance probability. So it's not accepted, it's accepted, 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 and not accepted, not accepted, accepted, not accepted. So in the first stage, those three spins are accepted, so they are flipped. And then we choose one of those three vertices with equal probability, one of the three. In this figure, we choose this leftmost spin with, with probability 1 over 3. So the chosen vertex is, the spin flip is accepted here. The other two spin flips are kind of rejected. So this goes back to blue, this goes back to red. So this is still based on a single spin flip dynamics, but they consider this algorithm promotes more spin flips than the conventional ones because you have more chances to have one spin flip. Fortunately, the red function for this, so first we have to take the log, divide this quantity by beta and take beta to infinity. That is the red function. The red function is identical to the red function for the Glauber and the Metropolis, which means that the argument minimum of UDA, so UDA is the virtual energy for digital annealer, is exactly equal to GS. So we should be able to use this Markov chain to capture the ground state with high probability. The reason why this identity holds is because you see, if tau is sigma x, so x is contained in S, there is this e to the power minus beta nabla x plus h is contained. So we extract this factor here in front of the sum. The remaining quantity is denoted by r. But since this is bounded from below by 1 over v and bounded above by 1, this quantity is bounded above by, this is bounded anyway. It's not, there is no singularity in the beta to infinity limit. So this doesn't play a role in the limit, and the red function is exactly equal to this. So we can use this digital annealer to find the ground state of the original Hamiltonian. But interesting thing is that in those three items, we are saying that this Gibbs distribution is not, in general, an stationary distribution for the transition probability. So we look at the difference between pi, the Gibbs distribution, and pi times the transition probability for dA. If this is 0, then pi beta is the stationary distribution for dA. But we have this explicit expression, and this is 0 when j is 0. But this is one-sided relation. And if we already know that j is not negative and h is 0, then we can actually reverse this direction. If pi is known to be the stationary distribution, j has to be 0. So it's a not interesting problem, right? All those spin variables are not dependent. They are independent variable. It's not interesting. So in general, digital annealer can be used to capture the ground state, but you won't be able to use this Markov chain to capture the first excited state or second excited state and so on, because the equilibrium distribution is not going to be Gibbs. I have this proof, but I'm not going into details. The proof is based on coupling and stochastic domination. If you're interested in the proof, then you can just access to this PDF by yourself. But I'm going to skip it. The most important thing is to show the performance of the digital annealer. So we applied this SA means that SA is a Metropolis algorithm. A single spin flip, well, DA is also based on single spin flip rule. But SA is Metropolis algorithm. We compare those two algorithms and see which one is better. So we applied those two algorithms to the max cut problem on the complete graph with 128 vertices. And we construct a max cut problem. So we construct this Hamiltonian where JXY spin-spin coupling is sometimes 1 or sometimes -1 or otherwise 0 with probability p plus p minus and 1 minus p plus p minus. So in this diagram, on the diagonal lines, this means that p plus, sorry, this is too small, I guess. This is p plus, this is p minus. So horizontal axis represents p plus, which means that this vertex, for example, with probability 1, jxy is always 1. This point, since p plus is 0, p minus is 1, so jxy is always -1. On this diagonal line, jxy is either 1 or -1. In this region, there is a possibility that jxy is 0. Okay? So each point, we compare those two dynamics is DA and SA, Metropolis algorithm. Gray region means that both Metropolis and DA can capture the ground state. It's equally likely. But in this region, so P plus, this one, so P plus is larger, which means that the Hamiltonian is ferromagnetic dominant. So there are many more ferromagnetic interactions in this region. In this region, we have lots of negative spin-spin interaction. So this is an anti-ferromagnetic region. And the ferromagnetic region, both DA and Metropolis algorithm can capture the ground state. But in this region, DA always wins. So this means DA is better in this respect than the standard conventional Markov chains. But still, DA is based on the single spin flip rule. So we would like...
I would say separation. But...
Separation. It's not clear yet. There is some fluctuation here. It's because of the finite time, finite range effect, I guess. If we repeat this many times, infinitely many times, instead of 128 trials, you'll be probably able to have sharper line, I guess.
Do you have an explanation why, such clear?
It's hard to tell. It's really hard to tell, actually. So as I said, this on the diagonal line, it's either 1 or -1, so it's kind of spin-glass phase. This is anti-ferromagnetic phase. This is a ferromagnetic phase. Somewhere here, that algorithm is more efficient in capturing the ground state, and we have no idea why this is happening for the moment.
Sorry, I didn't fully understand the figure. So what you in the different, so the parameters, I understand that was that for the J, for the probability for the interactions to be 1, -1 or 0.
Yeah.
But when you say it's more successful, so what do you plot depending on the color? And also there is never the green one, so I guess it's never winning.
Right. So we are repeating this Markov, this experiment 128 times, and then compare the number of successes. And so, for example, DASA. Yeah, to 20,000 steps. Yes, each experiment lasts 20. Exactly. Yeah, right.
So the DA systematically finds the ground state in the yellow part? Or
that's right. Yeah.
And also in the gray part.
Gray part too. Yes, in gray part, Metropolis algorithm also can capture the ground state, but in this region, sometimes Metropolis fails and DA sometimes fails, but most of the time DA can capture the ground state if we wait for long enough, of course. But there is some subtle issue. We are actually changing the temperature gradually. It's timing homogeneous Markov chain. I didn't explain this in my presentation, but I'm not going to touch this issue. But if you're interested in this exponential cooling schedule, the real statement is in this page, but I'm going to skip this page in my presentation. Time is, I don't have to, oh, okay. Okay, so the second one is the so-called stochastic cellular automata, or SCA. So the SCA transition probability from sigma to tau is defined by this. Here we are using H tilde. This is too small, isn't it? Maybe my eyes are very bad. Okay, now I can see it. So here we have doubled Hamiltonian here. So doubled Hamiltonian looks like the original Hamiltonian, but you have this extra factor whose multiplicative constant is Q. This parameter Q is called pinning parameter. Probably I can explain why this is called pinning parameter later. But you can see the relation between this transition probability and the Gibbs distribution. If we look at so this is a transition probability from sigma to tau. If we look at the diagonal entries of the matrix, so if tau is replaced by sigma, then this doubled Hamiltonian, so the sum of those two terms is exactly equal to the original Hamiltonian. And the last one, since tau is sigma, so sigma squared is just 1 because we are dealing with this Ising spin variable. So we are just counting the number of vertices containing the system. It's absolute V. So if we look at the off-diagonal entry of the transition matrix, so at least one vertex, sigma and tau disagree. And every time we have such a vertex, the energy increases by Q. So when Q goes to infinity, all those off-diagonal entries go away much faster, go to zero much faster than the diagonal entries. So the remaining quantity is just diagonal. And diagonal entry is just Hamiltonian. So you see the transition probability, when Q goes to zero, the only diagonal entries survive, and the diagonal entries are just Gibbs distribution. Now, the reason why we consider this a stochastic cellular automata is because of the independence. So here we have this doubled Hamiltonian. This term is the only term which is independent of tau. The other terms are linear in tau. So we extract this out here, and the other terms are summarized in this way. Okay? This is an effective field imposed on the vertex X. Now, this term is independent of tau, so that you can cancel this factor between numerator and denominator. So it's not going to show up in the expression. And the remaining quantity is because of this sum over x, you get exponential. So this transition probability can be expressed in this way, in the product form, which means that all spin variables are updated independently according to this acceptance probability. So this might be way quicker than the single spin flip dynamics. And since SCA can go from one spin configuration to another in a single go, this transition matrix is aperiodic and irreducible. And most importantly, this pi proportional to this one, this is actually in the denominator. This pi is the unique stationary distribution for the PCA transition probability because of the detailed balance condition. So let me explain this a little bit more. So as I said, that this is the denominator of the transition probability. If we multiply this one and transition probability, the denominator is cancelled so that only numerator survives. However, this Hamiltonian, doubled Hamiltonian, is symmetric with respect to the swap of the roles between sigma and tau. If you change the role of sigma and tau, they are still the same. So it's symmetric. That's why we have this detailed balance condition. And since this is aperiodic and irreducible, this must be the unique stationary distribution. So if we multiply this transition matrix n times and then go to infinity, this converges weakly to the stationary distribution, this one. Okay. Now, what we want to know is the rate function and the virtual energy, because that's what I explained in the previous, in a former page. The rate function is not difficult to compute because you can see that you just take the log and take and divide this log of this by beta and take beta to infinity. You get the Hamiltonian. This is coming from the numerator, and this quantity is coming from the denominator. Okay, so rate function is easy. And if I look at this expression, if we shift this to the left-hand side, like this, then this is equal to the doubled Hamiltonian. It's symmetric. So actually, this is equal to the same expression with tau and sigma swapped. So as you remember that as soon as we have this identity, M is going to give you the virtual energy. So now we know what virtual energy is. M is the minimum of the doubled Hamiltonian over eta. However, in the previous sheet, we have already seen that when Q goes to infinity, it is going to concentrate on the diagonal, which is the original Hamiltonian. So we can say that when Q goes to infinity, argument minimum of U is going to be GS. So we can use this multi-spin flip dynamics to capture the ground state of the original Hamiltonian. However, this Q, as I said, that this is called pinning parameter, the transition probability. So we have this factor everywhere, actually. And this actually makes the dynamics very slow because how am I supposed to say? As I said, that the off-diagonal entries of the transition matrix is exponentially small by factor e to the power minus beta q, right? Every time there is a vertex at which sigma and tau disagree, energy increases by q. That causes the exponential slowdown. So we don't want to take q extremely large, because we wanted to make it faster, but if we have extremely large pinning parameter, it's not going to be fast. So we wanted to reduce this the magnitude of q, and then in 2019, Okuyama et al. In Hitachi laboratories, they were able to show that q doesn't have to be infinity. If q is bigger than half of the largest eigenvalue of the matrix minus j, that's enough to ensure this identity. But still, j has to be large, depending on the spin-spin coupling. So this is one of the reasons why SCA cannot perform as initially expected. So we apply SCA, SA, DA to the same problem, the max cut problem of the complete graph with 128 vertices. Here, gray region, again, this is, so in this diagram, we compare Glauber dynamics and SCA. Here, both Glauber dynamics and SCA can capture the ground state with equally likely. But in this region, the spin glass phase, SCA wins. But if the negative spin-spin coupling is dominant, then a single spin flip dynamics wins again. So not all regions SCA can win, and this is unsatisfactory. DA was better than Glauber Metropolis, but we compared SCA and DA, and again, here we have gray regions, so there is a tie. And in this spin glass region, SCA and DA can capture the ground state. SCA more or less wins, but if the number of negative spin-spin coupling is bigger than the number of the other spin couplings, then dA again wins. Oh, okay. I should probably in a minute. Well, the last one is called Epsilon SCA. Actually, so as I said, that SCA has a negative effect due to the pinning parameter because of this. So it depends on the temperature in this way. So we wanted to make this independent of the temperature. So we define the transition probability in this way, and this is the transition probability for Epsilon SCA. And Epsilon SCA is like, how can I say, if we compare the transition probability for the SCA, in the SCA, all spins are flipped independently. But in the Epsilon SCA, we choose a set of vertices first in a Bernoulli way, so with a parameter epsilon. So those vertices are chosen with probability epsilon, and then all spins are updated independently. And since I do not have time, I'm going to quickly go into the last statement. This dynamics actually score is good. I mean, in practice, so we compare SCA and Epsilon SCA, for example. Gray region is tie. I mean, SCA, Epsilon SCA can capture the ground state equally likely. But in this region, Epsilon SCA always wins. And if we compare dA and Epsilon SCA, dA still wins when the spin-spin coupling are almost negative. But in this region, SCA wins. So Epsilon SCA may be a good algorithm, but unfortunately, we cannot actually show the identity here. We wanted to have identity, argument minimum of U epsilon. This is the virtual energy for Epsilon SCA. If this is equal, then we should be able to use Epsilon SCA to capture the ground state of the original Hamiltonian. But we have this one-sided relation. So if we use this Epsilon SCA, there is a positive probability that this Markov chain ends up in a spin configuration which is not in GS. So this is a negative side. So those 4 items are the hidden items in the middle, but now you can see that argument, this digital annealer can be used to capture the ground state of the original Hamiltonian. SCA can also be used, but the pinning parameter has to be sufficiently large. But the Epsilon SCA is still insufficient to say that we can use always Epsilon SCA to capture the ground state of the original Hamiltonian. But in performance, dA and Epsilon SCA outperforms the other Markov chains. So that's the conclusions. Thank you.
Thank you very much for this review of the different Markov chains. Are there any questions? Quick question, because we don't have so much time.
Question.
Oh, okay.
So do you have a quantified control how fast you can find out the capture the
Quantitative estimate. The answer is no. This is numerical. We have this two, how can I say, two approaches. One side we aim for theoretical justification. It's quantitative, qualitative estimate, and the quantitative estimate it's still insufficient. We just rely on the numerical simulations.
2 minutes.
Sorry. So in your case, basically you use the detailed balance? Maybe I missed it.
Well, detailed balance is one of the sufficient conditions. We cannot rely on detailed balance conditions all the time. It's just a sufficient condition. If we have some nice identity like that one. So this is zero temperature detailed balance condition. But this is a sufficient condition. If you cannot find a function f, you actually have to compute this virtual energy. But there's a formal expression for the virtual energy. So in principle, we should be able to compute what it is. But this is a complicated, I didn't actually explain this, but it's really complicated. So if instead of using this explicit expression, if we can find some function that satisfies the detailed balance condition, and that's the end of the story.
I think some physicists are doing some simulations using non-reversible Markov chain.
That's true. That's true.
I was wondering if your theory also applies to such.
That's at some point we started investigating this thing, but there are so many things to juggle at the time, so it was in a drawer and it's kind of forgotten.
Okay, well, thanks once again.